I'd like to turn it over to Christopher Kager, who is the Vice President of Strategy at GenHydro.
Thanks, Kim. So thanks all for coming, and thanks to the organizers. When I submitted this talk 6 months ago, I wasn't quite sure what to expect, and then when they accepted the talk, I realized I actually had to talk about something. So I'm actually a neurosurgeon, and I've had a long history of interest in green and renewable energy. I remember playing with the little electric transformers as a kid and, practically blowing things up, making hydrogen from water. I think I always secretly, Edward wanted to be a chemical engineer, but I went into medicine, and when I told my colleagues that I was being, drawn into this green energy company, GenHydro, they thought I was nuts, and I said, no, I'm actually really in my element. But-um-bum. So I've learned a ton, and I'm going to pass on. My task was to give a primer, Hydrogen 101, in under 5 minutes. So I mentioned I was a neurosurgeon. I also have ADD, so this is going to be a wild ride. And we'll save time for the panel and discussions at the end as well. Any questions as well?
All right, so again, we wanted to make sure that we started with an overview of hydrogen, what it is. I mean, you heard Edward specifically mention a couple of colors, right? And so there is a full rainbow of hydrogen that can be deployed to help us reach some of these climate solutions, and we thought it was important to start there before we got right into some of the discussion about where we might be able to use it. And so, Chris, go ahead.
All right, thank you very much. So 3 quick things I'm going to cover. What exactly is hydrogen? What are the different types or colors of hydrogen, and how can we use hydrogen for energy? So hydrogen is a very highly flammable gas, and interestingly, it makes up 75% of the universe. It's the lightest element, so it has the atomic number 1. It's colorless, odorless, tasteless, so you can't really sense it. It's been around since, or at least people have been aware of hydrogen since the 1500s. And unknowingly, Paracelsus created hydrogen, not knowing what it was. But it was Cavendish in 1766 that actually discovered that there was something flammable that they couldn't quite detect. So it's the lightest element, it's the most abundant element. Unfortunately, it's never really found alone in nature, so it's usually combined with something. Most commonly, oxygen. H2O is water. And it's also what most of the stars are made out of. We can produce hydrogen, since it's not found generally by itself, using multiple different methods, and each method has its own advantages and disadvantages. So we talk about a color system, and each method also has a particular carbon footprint which we can trace. So I'm not sure how well this exactly projects, but going on the left from left to right, it actually has the lowest to biggest acceptance and highest to lowest greenhouse gas contributions. So we mentioned blue hydrogen, which you can see there, generally made with something called steam methane reformation, and that does emit carbon, but there are carbon capture technologies that can be used. And then green hydrogen is really what our focus is, and it can be using any renewable energy source, or as Eric will talk a little bit about, using chemical type production. There's a special type called pink, which actually uses nuclear energy to create that, and that's kind of become having its own particular connotations and issues as well. So only green hydrogen has no carbon or greenhouse gas footprint, but unfortunately this only accounts for 0.1% of the current production globally of hydrogen. You may be familiar with the Department of Energy launching an Earthshot to try to increase the interest in production of green hydrogen, trying to get the cost down by 80% to $1 per kilogram in 1 decade. Luckily, we have a lot of novel technologies, including what we've been working on, that may already be below this. So what do we use hydrogen for? Basically, you got a little bit of a preview. Anything that requires energy. So there's a lot of industrial uses in steel, cement, chemicals, refineries that really could benefit from reducing their greenhouse gas emissions. Transport is a huge sector that's ripe for hydrogen innovation, direct heating, and then power generation as well. Think of hydrogen as an energy carrier or a battery. It has a huge amount of potential energy, and there's two basic ways we can take advantage of this potential energy. Direct combustion, which we sort of touched on with being able to get to 800 degrees Celsius. And interestingly, 1 kilogram of hydrogen releases 3 times more energy than a kilogram of gasoline. The problem is, as we'll see, that is hard to contain 1 kilogram of hydrogen. And then there's a second technique we can use hydrogen for, and I'm sure you've heard of fuel cells or fuel cell vehicles. That uses a very specific type of converter through another type of chemical reaction that splits hydrogen, and the electron actually forms a current, creating electricity. So for over 200 years, we've actually been using combustion engines using hydrogen. Multiple advances, obviously, since then have been made, and there are certain elements of the combustion engine that have to be different than a gasoline combustion engine compared to other types of fuels, including gasoline. So here's an example of what a direct combustion engine would look like. There are even some car companies now looking at direct hydrogen combustion engines. And on the bottom right, that's actually a General Electric turbine that's capable of burning direct hydrogen as well, or a blend, which we'll talk about. There are some issues with combustion of hydrogen that are still being worked out. There's a large volume of hydrogen that's required to reach many, many kilograms. It also has the potential to create nitrous oxide emissions, which have to be dealt with. And then there's the whole concept of producing the hydrogen, transporting the hydrogen, storing the hydrogen, that techniques are being improved upon regularly. So another type of use for direct combustion, this is actually that plant that's using the General Electric turbine. This is a plant in Ohio that is trying to go to carbon-free hydrogen usage. And they're trying to blend it with their natural gas to drive a turbine to create electricity. And initially they're looking at a 10 to 20% blend, but it will probably be the first hydrogen-only burning power plant in the United States over the next 4 to 5 years. Second type of use, again, we talked about fuel cells. These are very clean, very reliable, and a very quiet source of power. They don't have to be recharged like electrical batteries, and as long as you have access to hydrogen, can continue to run nonstop. And again, the way this works is that there's hydrogen through one part of the fuel cell and oxygen through the other. The hydrogen gets split into a proton and an electron. The proton can permeate a semi-permeable membrane. The electron cannot. The electron has to run outside another circuit, and it's that running outside the circuit that creates the electrical current that's then captured and used to drive whatever you need it to. So here's a quick example of a fuel cell type vehicle. You can see the storage in the back. It does have a backup battery system as well. And the key here, you can see there's multiple fuel cell vehicles that have been developed by Toyota, Hyundai, BMW. Hyperion was the sports car that I showed. Interestingly, that sports car, by the way, Hyperion, now they believe they're going to be on the market late this year or early next year. It's going to have a 1,000-mile range from one refill and go from 0 to 60 in under 2.2 seconds. So it's going to be a very high performance car. Unfortunately, that probably means very high price car. But on the bottom left, you can see there's certain advantages of even comparing a hydrogen car to a electric cell car. I didn't want to do that. And again, comparing the energy density, you can see that 1 kilogram of hydrogen is equal to about a whole gallon of gasoline. So you can get about 60 miles from a kilogram in a fuel cell vehicle, whereas the average in the US about 25 miles per gallon of gas. So when we talk about fuel cell vehicles, are we going to have enough stations? So this is an issue that is going to have to be addressed, the infrastructure. Because right now you can see the far left of the US is the only state that has any significant amount of hydrogen fuel type stations. So we're here about hydrogen. Why? Well, obviously we talked, decarbonizing the economy is no longer an option. We must do this due to progressive climate change. We don't think that total electrification of all of our power and industrial systems is going to be realistic. And hydrogen is a very versatile carrier or energy storage system, and it can help decarbonize those sectors that are very difficult to decarbonize. You can see these sectors here. Over the next 10 years, they expect hydrogen usage to double or triple to over 200 megatons by 2030. And why now? So there's been these peaks and valleys in the life story for hydrogen. Through the 2000s, people thought, hydrogen was going to be the next great thing. It was on the cover of Time. But now there's been an explosion of technological advances, as well as pressure from environmental and political drivers. There's been an amazing increase in the methods of production, driving down the cost, and we're happy, thankfully, to be part of that. We can definitely decarbonize overall the production of hydrogen as well. And so all of these changes and the change targets are leading to governments and companies to seek better decarbonizing solutions and to increase the scale and decrease the time frame for which this is happening. So that's my 101. We'll have a quiz in a little bit.
So thanks for setting the stage there, Edward. Maybe Eric, you can talk a little bit about where you guys have been on some of the various colors of hydrogen.
Sure. Yeah, and I think to a degree we agree that there's going to be this ecosystem of colors, as I had mentioned initially, and there's going to be a transition period. And what's interesting about each color is that there's pros and cons about all of them. And so, as Ed had mentioned, there isn't a green technology that is at scale right now to meet current demand. And I think if there was, that would be employed, right? And that's certainly something that we're working on, and we have a model that's built around that. At the same time, on the blue hydrogen side of things, there's things that we have to consider. And so having easy access to call it asset infrastructure that would allow us to produce vast amounts of hydrogen today is fantastic. But then we also have to make sure that we're doing the proper level of analysis all the way up the value chain or supply chain. And that would mean what kind of CO2 carbon capture systems are being put in place today? What are the techno-economics around that? Where's the power coming from if there's, let's say, an electrostatic precipitation version of that, or if it's chemical absorption? What are the economics around that? Implications of that, and then looking further up to where are we looking at when we're fracking for natural gas to begin with? What are the implications of methane leakage, right? And what are we doing for that as well? And so I think it's
fair enough, but I don't think we want to go too far down that road.
Yeah.
Because frankly, if you go down that road for a lot of the green hydrogen technologies, you'll find that producing silicon panels in China from coal-based power isn't very clever either. I think all of these put together, there are solutions in any of these places. We would certainly agree with you that better emissions control of fugitive emissions from natural gas wells is something that should be done, as do most of the major oil companies, by the way.
Yeah.
So I think the point is, it's not very clever or helpful to throw shade on any one type of hydrogen. I think what we need to do is move towards an infrastructure that values clean, including all scope 1 through 3, including all parts of the value chain, and values competitiveness and values timeline. Because what we need to do is get this started and get it started in a time that allows the growth of these products sufficient to meet the 2050 transition.
Well,
I was going to say, the only thing I would add is I agree with all of that. I'm a numbers guy. So I think that you have to have a proper accounting of all techniques. Right. You have to know what you're making, what the cost is, and how you're using it to abate, and then use subsidies or governmental carbon credits or whatever to push those technologies or methods that are, you know, less carbon intense forward. But you can't do that without knowing the full costs.
I don't know if some of our panelists want to talk about scalability, because I think that is a huge question about, well, some of these technologies at least exist on a very small scale right now, but it's going to take a considerable amount of effort to scale them up to something that is usable kind of worldwide.
So I think Eric covers a little bit of that in his slides.
Okay.
Yeah.
Do you want to fast forward? You have the thing.
And maybe
Sure,
Edward, do you want to just kick in first?
Yeah, I mean, I'll just say, I mean, just broadly, I mean, as I said, we produce about 7 gigawatts, so 7 kind of nuclear scale plants worth of power and steam globally. We buy another 2 and we sell another 2. So we consume 7 and produce about 9, sell 2 of it, and then produce another 2. So that scale allows us to, you know, when we build a new facility, we'll put in a new power plant to go with it. About half of the emissions of Dow come from the power and steam in the power and steam sector, and about half from the process. So the hydrogen that you can build with blue hydrogen with an SMR and you know,
For the audience, SMR?
steam methane reformer or an autothermal reformer, which is an ATR, I guess. And those are big kind of process units that remove the CO2. They basically take methane and give you hydrogen and CO2. And you put the CO2, you store the CO2, sequester the CO2, and you burn the hydrogen in your process and then create water, and you do that. And that process is scalable now. Carbon capture is something that, you know, we've been doing for a few years in Canada at one of our facilities, and we've announced a world-scale ethylene project we'll put in there by 2030. So that's something we can do now, and we are planning on doing now at both our facilities in Fort Saskatchewan, Canada, and also in Terneuzen, Holland. So I think I'll leave it at that. You know, remember, the point is hundreds of megawatts of scale is what you need to deal with an industrial facility of the size we're trying to deal with.
Yeah, and if I may chime in, and maybe just for the record, I'm an equal opportunity shade thrower. And so, and the point I was trying to make, and not to throw shade on any one color, even though we do focus on green, is that we have the same level of scrutiny and analysis on green as well. And that's why we're working with some large organizations, for example, with our technology, which is more of a solid fuel-based technology that produces hydrogen chemically. We're working with actually spinning up the value chain of that, where that solid fuel is made originally is actually going to be produced by hydro and sun or wind. And so we're doing the same thing, and we realize how much that's going to take, for example. But to the point of scale, I think that it's good to do that level of analysis on each color and then say, okay, it's going to take a certain amount of transition and scale and a certain amount of sunk capital asset costs as well as we're transitioning to different types of fuels and maybe upgrading our infrastructure, for example, because it is a different type of gas, that we just do the proper analysis on what we have today, what scalability do we have, and then what are the implications up throughout the entire value chain. And I think we need to do that kind of analysis and then determine what is that ecosystem going to look like and where are we going to put our dollars today. And I know at least with covering GenHydro, covering the green bubble of hydrogen, we have projects that are slotted right now for producing hundreds of megawatts by 2023 in green electricity production and 20-30 tons a day of hydrogen. And what we're doing is the compounds that we're using, which predominantly are specific kinds of alloys, we're actually sourcing them from what they deem to call a post-consumer product. So we actually source them from landfills, and so ionic compounds are essentially different types of metal alloys, and we use an oxidation or redox process that is absolutely scalable in an array or a system of units. And so what we do is we actually, to kind of deal with some of the issues around those alloys originally being made in a carbon-intensive method, is we source them from scrap. And so it's a post-consumer product. It may have had a 30-year useful life on an automobile, for example. And then now we can take that back out after it's had a post-consumed life and pull out 80–90% of the energy it took to make it. And so that's the way we're taking that incremental step in trying to decarbonize up the value chain, or at least mitigating that as much as possible, and then working with some larger players for scaling. But it's certainly going to be a method for getting there. And I do think that there's going to be an ecosystem of solutions. But I would say for sure that what's great is carbon capture, for example, can be 99% efficient, which is phenomenal. And that's at the SMR level. That's where you take natural gas through steam or form methane and you crack it, like he was saying, and you can separate the CO2 and the hydrogen. It can be 99% efficient, which is great. But I don't think the analysis should stop there. You know, I think we should also say, where are we getting that? What do we have to do to continue to decarbonize up the value chain? And we openly admit that even our system is not 100%, but we're doing what we can, for example.
Is a hydrogen, and that hydrogen we recycle in our plants. And so a lot of what we're actually talking about, we call it blue, but in a way it's not really, it's actually recirculated.
Because it was just going to be lost anyway. You're capturing what would have been.
It either would be used for heat in the furnaces, or it could have been flared on occasion. But for the most part, the process integration of our facilities is such that we would use it for heat in any case. But that circularity is part of what we're also trying to do. The other thing that's critically important is, and we haven't really talked about this very much, but the best way to reduce energy and emissions is to consume less energy. And so, efficiency and reintegrating the facilities. A modern cracker is massively more efficient than something 40 or 50 years old. And so 50 years ago, we needed lots of steam to kind of run crackers every day. Today, those crackers produce steam, using potentially the hydrogen as a source of heat for export. I do think,
that's a good point.
To your point, I think it's incredibly important to, it's very geeky and it's very nerdy, but you really do need to count every part of the phrase, the steps, and figure this out. And you need to figure it out in a way that, nothing we do is going to be perfect, and we shouldn't let the perfect be the enemy of the good. You're going to have to get stuff going in the next few years, and that's part of the kind of, we put together a path to zero, which is out on our kind of website. And the point is, we have a hypothesis of how over the next 30 years we get to zero, and we did it by asset, okay? A lot of that has to do with hydrogen. We're not particularly interested in being a hydrogen company. That's not our base. We'd much prefer that others go in that direction.
Let's talk.
And we think that building a public infrastructure to support that hydrogen is a critical thing to allow companies like Eric's to have a market to sell into, and the standards of what they're selling, so how clean and in what way, and how's it measured with a consistent approach that we've talked about a lot. And then, I need to have, my problem as a guy who provides power and steam for crackers is if it blips, even for a cycle or two, you wouldn't even notice it in this room, our facilities may have to come down because you lose motors and you lose circulation in your big furnaces, and it gets very expensive very quickly. So we need reliability, which means that I need not only Eric's company, I need 55 other companies feeding into one common hub and grid, where there's just like the natural gas grid at home or the power grid at home. We're not all relying on one facility, right? We're relying on hundreds of turbines across dozens of companies in multiple locations. You're going to need the same level of sort of integration and integrity in a hydrogen system. And you got to get there, not in 50 years or 70 years, but in a shorter period of time.
And I'm glad, Edward. I'd like to maybe shift our discussion just a little bit on, we talked about scalability a bit, but what we haven't talked about is, the role of the regulatory and legislative climate to be able to help that possible. Because, companies like Dow, where Edward is at, as well as companies like GenHydro, can, help advance this technology, can apply this technology, can invest significant resources, but they are individual companies, right? And so not only does it take the collective might and effort of our chemical industries and innovative industries as well, but it also takes the initiative of federal regulatory schemes to be able to support this process. So we know that under the current administration that, they have recently passed an infrastructure bill that includes a number of key areas and a significant amount of resources to various regulatory agencies to help support some of this process. But do you all see any barriers that currently exist or that would be helpful, from a regulatory or a legislative landscape that would help improve like the processes that you have in place if you had some, some incentives or at least some, some support from the federal government or legislative arms?
Do you want to go first, or do you want me to?
I'm happy to, because we've actually been, especially as a renewable energy technology company, we've actually been facing some of these challenges where we say, where is our competitive market space? And how do we stay afloat economically? Right? And so if we're producing green energy, which typically has a price premium on it, and it costs more because it's not scaled just yet, how do we make sure that the company is staying afloat so that we can continue to do what we're doing? And so we've looked at some of the subsidies or regulatory activities around that, and actually have connected pretty high up with DOE, Jennifer Granholm, and even some of our local representatives on starting to bring that conversation up. And what we found is, at least for us in our perspective, we've done a lot of work in building out our model and vertically integrating where we need to, so that we can cover our costs for green renewable energy in the form of hydrogen that is at price parity with natural gas today. And so we can match that price for the same amount of energy density today without any government subsidy. And that's been our focus and our perspective, because we don't want a policy shift or regulatory shift to squash that good work, at least. But I do think that there is a place for, at the markets and industry, and that's our perspective, and that's what we've tried to do in-house. But I think that there is a place for that at scale, because GenHydro can't provide green hydrogen to the world, for example, as much as we'd like to. But in that ecosystem of colors and energy suppliers, that there's going to need to be, I think, some regulatory pressure to incentivize organizations to change. And then I know a lot of organizations are starting to have just that natural, socially conscious ESG focus, which is good from like an optics perspective, which is very much driven by the mass markets, which I think is a fantastic shift. But at the same time, I think there's a lot of investment that's done into infrastructure that's made by the government, for example. So I think there's going to have to be this tight-knit, hand-in-hand, multi-dimensional approach to actually shifting and transitioning over time.
And very briefly, production subsidies, tax credits, carbon credits, there's a lot of different things that can be useful economically to drive that forward.
Right, right.
Yeah, so I mean, we would agree in a large way. I mean, I think there's maybe 5 things from our perspective. First off, you're going to have to get the value of low-carbon solutions through your value chain. As I mentioned earlier, a market-based, economy-wide price on carbon is probably the simplest and most effective way, in my view, of doing that, but there are other ways. The second thing I'd say is, once you have that, you have to protect domestic competitiveness, because if you're going to have a carbon price in your economy, you can't have others dump products made in economies without carbon prices on your economy and kind of be free riders. I think that's, you may have heard of carbon border adjustments or these sorts of things. That's another way to do that. I think you need to have a national strategy to incentivize, to fund, and to build the infrastructure. I think we both agree that you're going to need hydrogen infrastructure, you're going to need carbon capture infrastructure.
Yeah.
Probably going to need hydrogen storage. You may need more batteries in the power grid. You may need more wires for the power grid. You're going to need different technologies in your power grid to preserve things like spinning reserves and all sorts of other technical aspects of the grid. I think you need research partnerships at national and even multinational levels to help fund new technologies.
Absolutely.
And then I think you need multinational agreements that probably enable cross-border movement of hydrogen. It's not clear to me that every region, let me put it this way, it is very clear to me that there are going to be winners in green hydrogen, winners in blue hydrogen, and it may be that one part of the world is advantaged on green, another part is advantaged on blue, a third part is advantaged on pink, and somebody else does something else, and then there's another part of the world that's effectively energy poor, but maybe has intellectual capital rich. And so hydrogen will flow just like natural gas and oil do today. And we're really, as a company, interested in, involved in all of these solutions and these technologies. And we're really looking to do things differently because that's what we need to meet our goals of being carbon neutral in 2050 and even to take 5 million tons out of our emissions by 2030. That's not a small problem when you're trying to grow.
That's fantastic. Yeah.
So.
Yeah, and one of the things that I heard very clearly from both of you was that this is a multi-stage and multi-level effort, right? I mean, as a scientist, the research piece, I think, is critically important, and that's going to involve both public and private partnerships. So you're going to have real concerted effort to say, here are some technologies that we really want to try to move forward, that either they're at the infancy and we need to figure out a way to fast track them, right? And so we talked a little bit, I think Eric and Chris talked a little bit about DOE. And so we know that DOE has a relatively extensive program, and given the fact that they have recently gotten a considerable amount of resources associated with the infrastructure bill, that they have put out a lot of calls for information. I think Chris mentioned the hydrogen shot, right? And so the Earthshot project, where they were really looking for information from industry and others about how do you advance hydrogen technologies and move them forward. Are there specific projects that should be an area of focus? Are there specific efforts like looking at hubs and locations that should be a specific area of focus? I know they continue to do that among a number of areas. I know they have recently just put a request for information out related to the manufacturing sector. And so really looking again to try to identify those technologies that may help us reach some of these goals sooner and quicker, right? So they can figure out as an agency where to focus their time and attention and where to maybe put resources in to some of those initial scale projects and then help companies scale those efforts up. And so it really is going to take a lot of different efforts. I mean, I know that Edward specifically mentioned the hubs, and so that's going to be critically important, is to be able to have regional locations where companies can actually plug in and coordinate and connect on how they capture the hydrogen and carbon that they need to be able to utilize in their processes. And so this is not just a one-stop shop solution, and I know everybody likes to think that there is just a silver bullet out there that is going to help us reach our climate goals, but there are a lot of things that are going to help us get there. The other thing I heard, and I know we only have about 10 minutes left, so I want to make sure that we open up some time for questions here, but one of the other things that I heard from this group is that it is very much a matter of not only our industries, right, which are similar but different, right, as you've heard from some of the discussion here, but also other industries, right? So this is not just one industry's problem to solve. As well, it's not just industries, collectively problem to solve. Everyone, including you in the audience, is going to have a stake in this, and we all have to figure out where are the best solutions, where can we focus some of our time and attention, and it's not going to be in one area. And so we really have to make sure that we're looking across the board at all the technologies that exist and really trying to facilitate that process to happen.
Hey, how you doing? Thanks. This is great information. My name's Tim. I work for a transportation company called Vontier. So I'd love to hear more about what you talked about earlier, where California is, they've always been a leader in driving innovation, driving acceptance, and then that spreads across the U.S. and eventually around the world. Do you know anything about what California did specifically to get that hydrogen vehicle infrastructure to the point where it's useful? Did they have a lot of subsidies? Was there grants given? Did you have any info? Anybody?
So you hit the nail on the head. A lot of money. So I don't remember statistically. I think they have something like 80 consumer refueling stations or something like that.
42 with another.
It's going to be 60 by the end of the
Oh,
year.
yeah, 60 by the end of the year,
That's
but then
right.
the 117 is the goal.
But they have a set
And like,
amount of money that they've put into that every year
Yeah.
that's in the tens or hundreds of millions of dollars.
So there's something on that called the hydrogen, the California Hydrogen Fuel Cell Partnership, that a lot of private sector organizations, namely Toyota, for example, are a part of that, and that's kind of where a lot of these initiatives funnel through. And so they work hand in hand for regulatory side of things and permitting, but then also a lot of the funding has been coming from private sector. And one of the ways, for example, Toyota gives a $15,000 fueling card to
It's like
every single person.
Free hydrogen, right?
Right, for
3
free
years or
hydrogen
6
for
years.
like, it's like 3 years worth of driving for the average consumer. And that's one way that they're trying. So they're funding some of the infrastructure, though not as much as like Volvo and Daimler Chrysler will be, for example. They have a new partnership in Europe. But then they're also enabling a more frictionless transition for consumers, for mass market. So I think that both legislative and private sector have come together.
If you haven't seen it, look up High Deal.
Okay.
So LA
Yeah,
is
they're a big part.
becoming the first sort of independent hydrogen project city in the US. And there's a green hydrogen coalition leader that's sort of.
Okay, I'll try to be quick. My name is Kim, also from Toronto, Canada. I run an incubator of ambitious teenagers that are learning emerging tech and applying it to big problems. They focus a lot on many different things. I know we have some that are interested in this sort of thing, but generally speaking, what areas would you suggest that a 15, 16-year-old be looking at if this is the industry that they want to work in? And what are some problems they can potentially help solve with their creative minds and knowledge in machine learning, all of these things?
So I have a 21-year-old who's very interested in this, and I can kind of talk to what
Yeah.
I've kind of guided her to. I think this is an enormous problem. It's the problem of our generation, right? It requires social issues, it requires political skills, it requires technical skills, it requires passion, but it also requires application. Every 15-year-old thinks passion is enough. It isn't. Passion isn't even a ticket to the door anymore. Get the technical skills, but don't ignore things like writing. In my generation, you could get away with going to some of the I won't choose names, but some of the really nerdy schools and not really writing. That's gone. This is a societal problem. It has to be addressed. You need affordability, sustainability, reliability. It has to be politically possible, and it has to be scientifically possible. You have to cover all 5 of those things to solve this problem.
So on a technical level, would you say it's more like chemical engineers, or are we talking more like software?
I think it's all of the above, right? And Kim, I will say as well, like we as an industry last year in 2020 actually launched a project called our Future of STEM Scholars Initiative, which is actually directly focused on incoming college freshmen studying STEM disciplines, really to get them in the STEM disciplines, tell them about our industry and sustainability and how they can apply that, and actually shepherd them over those 4 years with scholarships, as well as mentorship opportunities and internship opportunities. Because we see it, as Edward mentioned, as a long-term and concerted effort even from that level.
Okay, maybe.
Hi, Joshua Johnson with Meta Hydrogen. I was just wondering, we're also doing some things with IoT things. How do you see IoT and basically quantifying going green around green energy and quantifying or rethinking carbon credits and the whole industry of what it means to go green and green hydrogen and being a part of that? So commoditizing hydrogen, for example, data-driven financials, et cetera, connecting it to exchanges and connecting it, like say BlackRock, if they're doing an investment, how do you quantify if it's really executing based on the parameters of what it said it was originally going to do to go green. So how do you see IoT and technology and infrastructure in general playing a part in this to quantify with data, proving that it is different, for example?
Sure, yeah, because I've got some thoughts on that. We actually we just got partnered with a firm that is working with a pretty large exchange called Macquarie, and there's only a few exchanges, by the way, that deal with hydrogen, let alone the various different colors of that commodity. And I think one of the things they're doing is they're doing confirmation of origin, where there's a vetting process, as Ed had mentioned earlier, of just basically making sure that the hydrogen was produced a specific way. And so the most likely will be various colors that people can purchase and jump into. There's also I think maybe.
Josh, I'm a chemical engineer, so interested to learn more about the process. What do your product yields look like? How much hydrogen do you get out per ton of input? And then I would guess that there's a limited supply of high quality post-consumer whatever your input is, so what scale can you really reach?
Yeah, that's a good question. So for our alloys that we prefer, then there's a range of them. Number one, at least on the scrap side of things, so post-consume products is about 33 million tons a year that is available. And what we're working with some larger organizations to start to vertically integrate so that we can just start to recycle that, because it's an oxidation and redox process, so we can actually reverse the oxidation process and use it again. And the goal is to use that with a hydro dam or wind and solar, and then just have better ways of distributing energy in the form of a solid fuel, which makes it easier. You don't have to compress it, it's much more energy dense, et cetera. Plus you get two forms of power, direct electrification and hydrogen. So for 1 ton of our material going in, we get 111 kilograms of hydrogen coming out and 6.6 megawatts of direct electricity.
Thank you.
No problem.
So we are already out of time. That hour flew by. So I just want to thank our 3 panelists.
Absolutely.
So thanks, Chris, thanks, Eric, and thanks, Edward.
Thank you, everybody.
And thanks to Kim.
And thanks so much for our audience and the questions that you had. I think this was a really good discussion, but I want you all to leave with a clear message here that while we were focused on hydrogen, as you heard throughout our discussion, that's not the only technology. You heard us talk about carbon capture, heard us talk about modular nuclear reactors, electrification of crackers. So there are a number of technologies that are going to be needed to help us meet all of these goals here. And this is one critical one, but it's not the only one. So thanks so much.
Fusion.
Exactly, right? And so, again, thanks so much, and I hope you enjoy the rest of the conference.
Thank you.